Okay, today we're going to be looking at forces again and how they relate to objects. This next unit we'll be playing around with friction and resistance. So your bell ringer question here is, what is friction and what does it do to the movement of any object? This question should be in Google Classroom. So friction is a resistive force, okay? So if we think about of something on the floor and you have a box sitting on the floor and we have a person pushing the box that way, it's not going to move very well because of the contact with the ground. There's going to be friction exerted back on the box. Okay, so what does it do to the movement of any object? It slows it down, it resists the movement. Okay, so there's our learning goals. We're going to look at systems and stuff again. And we can watch the video here in class when I come back. We won't watch it today. But we have all the different systems we're going to hit. We're going to have mechanical systems, so like the car, all right? We have fluid systems, so an airplane is actually in a fluid system because the air is the fluid. Okay, we've also talked about that before with liquids. All right, we have electrical systems. All right, and that's actually a resistor there, which slows the flow of electricity. And then we have thermal systems. That's a thermos, which you guys know that a thermos slows the cooling of any object. Okay, so those are our systems. We're going to be kind of looking at each one of those this unit. So if you remember from physical science, we had this guy named Isaac Newton, and he has some laws. Okay, so we're going to review those and see what we remember. So Newton's first law of motion is every body will remain at rest or will continue to move in a straight line with a constant speed unless acted on by a net force. Okay, this is, if you remember, Newton's law of inertia. Okay, something in motion will stay in motion unless acted on by an outside force. Okay, so anything that is moving, it will continue moving forever unless there's some outside forces in play to slow it down. So this is kind of theoretical, but it's actually happens in space. We have satellites going around the Earth. They're going thousands of miles per hour, and they just keep going and going and going and going because there's nothing slowing them down. They're caught in a loop around the Earth in our gravitational field, but there's no resistive forces up there that's slowing them down, so they can maintain that speed and they can stay above the Earth. So Newton's second law, this one is the one that is used the most often in calculations. Okay, so the acceleration of an object is directly proportional to the net force acting on an object and inversely proportional to the mass of the object. So we have this equation here, force equals mass times acceleration. We're going to be using that equation here quite a bit. Okay, and we can also rewrite that if we wanted to. We can solve for acceleration here by dividing by the mass. So acceleration equals force over mass. And maybe we don't want that equation. Maybe we just want to solve for the mass, so we can divide by acceleration. Okay, and so mass is equal to force over acceleration. And you can use any variant of the equation there that you would like to. Okay, so this is another way that we can calculate acceleration. If you remember, acceleration before was change in velocity over time, which we can still utilize that if we wanted to, but we now have an acceleration equation that relates it to forces. Okay, so just like pushing the box in the last example or pushing a brick in this example, you apply a force to an object, it makes the object move. Okay, so in the equation there, the net force is equal to the product of the mass and the acceleration. Okay, so another thing we can write down here, it's very similar, and we've talked about it before, but you might not just have force equals mass times acceleration, you'll have net force equals mass times acceleration. And to kind of give you an idea what this could be, you could have maybe somebody pushing on an object, or maybe you're throwing something downward, so you're going to have force of that push or the throw, and then you're going to have gravity as well, so force due to gravity, that's going to equal the mass times acceleration of the object, okay? So you can have several forces involved, but then you have an overall net force of the object. So a couple ideas here. Twice as much force produces twice as much acceleration. So if you said that one hand is going to have a 2 meters per second squared acceleration, then your force of, let's say, force of hand 1 plus force of hand 2, that's going to be 4 meters per second squared. So your net force, relating that back to the last one, would be 4 meters per second squared, which is both of those hands pushing on that. Okay, so another example off to the right here. Let's say you have that one hand that's pushing 2 meters per second squared, but you have 2 bricks. All right, so that's going to give half as much force because there's twice as much weight. So your net force in this case would be equal to 1 meters per second squared because of twice as much weight, okay? And the examples below kind of show you that as well, okay? So you got your 2 hands here, 2 bricks, that's just going to be your normal net force, 2 meters per second squared in this case. And then over here, 1 hand pushing, 3 bricks. So that means there's 3 times the mass, or 1/3 as much acceleration, so that would cut you down to 2/3 meters per second squared if we're looking at numbers. Okay, you remember from previous lessons, the metric unit or the SI unit for forces is the Newton. Okay, and defined Newton is a force which accelerates 1 kilogram of mass 1 meters per second squared. We talked about that before, just kind of remember that. Okay, so net force, I mentioned that already. Okay, another way to write that would be sigma F here. So sigma kind of looks like this, and F, that is the same thing as net forces. So that's all the forces added together into one. All right, the second law of motion is what you got to think about when you're using net force or when you're trying to figure net force, okay? In this scenario here, you're pushing a bus. All right, we don't have any friction involved yet, that's coming. But we want to figure out the force involved. You have a 2,000 kilogram mass that you are accelerating 0.05 meters per second squared. And we want to figure out what is the applied force to the van. All right, well, let's figure this out. So our net force, or our applied force, or our net force, which is the applied force, I suppose. Okay, so they're the same thing, is equal to mass, which is 2,000 kilograms, times acceleration, which is 0.05 meters per second squared. You just multiply those two, so our force is going to be equal to 100 newtons. Okay, so you just multiply those two numbers and you get your net force. Simple as that. All right, so the third law of motion, you might remember this one, is equal and opposite reactions. Okay, so for every action there is an equal and opposite reaction. For this example, you may have been on a boat before and kind of stepped off of a boat onto a dock. Okay, let's put a dock right there. And you notice that the boat swings away from the dock as you step onto it because you're pushing with your foot here to step onto the dock, so the boat has to go that way. So you have an equal and opposite reaction. Now, a really interesting kind of force involved here is this scenario here. You're pushing on the wall, say you're pushing on the wall with your finger, and the wall is pushing back. The wall does not flex, right? In this case, the bricks did not move. So you're pushing on the wall pushes back. Those are equal and opposite reactions, okay? And there is an interesting force here called the normal force. All right, and we'll say here that the normal force is equal to the force of your push with your finger. So the normal force is what is basically a surface force. So a surface counteracts whatever force is happening on it and pushes back. If you think about maybe some way you've used the normal force before, let's say you have a container, right? And you start setting a lot of things on the container. And at first it doesn't really do much, but then the container starts to compress a little bit, all right? And eventually the container gets down really small and maybe cracks and breaks. So there was a certain amount of normal force that that container could handle or could exert back before it broke. All right. Another way to think of the normal force would be like a trampoline. All right. So your trampoline with nothing on it just sits there like that. When you start bouncing on it, or you have a person on it, something on that trampoline, okay, then your trampoline starts to flex. But it doesn't break, right? The trampoline exerts a force back up on you, and you're exerting a force down on the trampoline. So this would be the normal force in the case here, all right? So normal force is a surface force. Well, let's check out an example here. A force of 3,000 newtons is applied to a 1,300 kilogram car at rest. So the car is not moving, all right? We want to figure out what the acceleration is. Well, we can use Newton's second law here to figure out the acceleration. We don't have to use our velocity final minus velocity initial, that kind of stuff again. We can just use our basic force equals mass times acceleration. That's quite a bit simpler than what we've done before. So your force is 3,000 newtons. Your mass is 1,500 kilograms. And our acceleration is what we're trying to figure out. So a little math here, a little algebra. Divide the 1,500 over from both sides. And we get an acceleration of 3,000 divided by 1,500 is 2 meters per second squared. Okay, now the next question, what will its velocity be 5 seconds later? Okay, well, we kind of have to understand how acceleration works, because acceleration says I'm getting 2 meters per second faster every second. So at 1 second, let's say 0 seconds, we're going 0 meters per second. At 1 second, we're going 2 meters per second because of our acceleration. At 2 seconds, we're going 4 meters per second. And then you could see what's going on here. So we have 6 meters per second at second number 3. Second number 4, we're at 8 meters per second. And second number 5, we are going 10 meters per second. So that's how fast we're going 5 seconds later. Okay, because every second we accelerate 2 meters per second more. So that's how you use the acceleration there. So let's check out another example here. A 1,000 kilogram Ford goes from 10 meters per second to 20 meters per second. What is the force acting on it? Well, now we kind of have to relate some things back to our previous equation, right? Because we're trying to figure out a force, but we only have a beginning speed and an ending speed. We don't have really a acceleration that we can figure here, all right? Or we don't have it like the last example. So we have to actually calculate it using our previous acceleration equation, which is velocity over time, okay? Well, that is a final minus initial, so 20 meters per second minus 10 meters per second velocity over 5 seconds. So that's 10 meters per second difference in 5 seconds, which is a 2 meters per second squared acceleration, just like the last question. All right, so now we need to use that number. So we have the 2 meters per second acceleration, and we have the mass right there. So now we're using our force equation in conjunction with that acceleration equation, okay? Because we're trying to find that force acting on the car. So 1,000 kilograms times my acceleration of 2 meters per second squared. The force applied on the vehicle is 2,000 newtons, okay? So this is a way you see how we used our previous acceleration equations with our new acceleration and force equation, so Newton's second law, in order to calculate forces on an object. Okay, so reminder here, weight. We've talked about this before. You might remember a lab where we used a spring. Okay, we had to calculate the weight of the mass there, which is mass times gravity. So weight is the gravitational force on an object, right? It's how much gravity is pulling down on something. So weight is a vector quantity, which means it has a size and direction, okay? It's different from mass, which is a scalar quantity, which it just has a magnitude or a size, okay? And we've discussed this before, but the weight of a body varies with its location near the Earth, which is kind of interesting. So if you are on the top of the highest mountain on the Earth, you'll weigh a little bit less, okay? Or if you're at the bottom of the deepest trench in the ocean, you'll weigh a little bit more because you're closer to the center of the Earth. So if we remember, weight, gravity, usually is written as g. So acceleration due to gravity is 9.8 meters per second squared. Depending on the scenario, that could be a negative, but we use it as a positive for most of the time, and we just state positive as downward, okay? So that's acceleration downward due to gravity. So a couple things to think about here as we wrap this up is what happens to weight on an elevator? What happens to your weight on an elevator, okay? Well, let's look at all the forces that are involved in an elevator. So I'm going to draw what's called a free body diagram. So if we are on or in an elevator, we have gravity pulling down on us, all right? And then we have that force that I told you guys before, which was normal force. And we're not going left and right at all, okay? So we're just going up and down. So let's say for this scenario right here, the elevator is at rest, it's not going anywhere, and you're just chilling, pushing the buttons, waiting for it to get started. Okay, so let's say our elevator starts going upward. What happens to the forces involved, okay? So let's forget about this stuff over here. All right, so your acceleration will be upward, all right? So think about, so this is our scale over here. Think about what's gonna happen to that scale as the elevator starts to go up, all right? Think about what happens to your mass as you go up, as the elevator starts to go up. So the elevator here is starting to push up, right? Your body wants to stay where it is, so it's going to exert a force down, right? It's going to continue to exert the force down, but it's going to be more. So if you're thinking about a scale on an elevator, okay? So the scale on the elevator is going to read a larger weight than what you actually are because of your inertia, right? So the elevator wants to move up, but you want to stay where you're at. And so that scale is going to read a heavier number because of your inertia. You want to stay where you're at, right? You want to resist the motion. So scales, okay? A scale does not read your actual weight. It measures your force applied to your body, okay? The upward force applied to your body. So the scale really is kind of seeing what the normal force is in there compared to your body. So let's look at another scenario. All right, so you're going to go down now. The elevator starts to drop down underneath you. All right, so what happens? So right here is the scale again. Elevator starts to go down. Remember what your body wants to do. Your body wants to stay where it is, right? So when the elevator starts to go down, it really kind of it drops beneath your feet. And so you kind of feel a little bit lighter, right? So if we're looking over here, 700 is your normal force when it's not moving. 400 might be your force here because the elevator is dropping down below you because your inertia wants to keep you where it is. Elevator is dropping down. So you're going to read a little bit lighter here in this scenario. Okay, let's look at one more. So let's say the cable breaks, the worst case scenario. What happens then? The elevator is much more massive than you are, right? So that elevator is dropping down and the scale is connected to the elevator here, right? So if that elevator is much more massive than you are, then that elevator is just going to drop beneath your feet and you will just be sitting in the elevator, like hovering above the floor, and you will feel weightless, okay? So that is weightlessness, when everything drops beneath you, or say you're falling, you're free falling, and you just kind of feel like you're floating, all right? That's weightless. So all of these scenarios here, we're considering inertia, right? You're considering the tendency of your body to stay where it is. if the elevator drops below you, okay, let's say it doesn't break, it just drops, it's accelerating downward, you're going to feel lighter because your inertia wants to keep you where it is. If the elevator goes upwards, you're going to feel heavier because, again, your inertia wants to keep you where you are, all right? So I just mentioned in the last slide there, weightlessness and free fall, all right? So when in free fall, gravity is the only thing acting on an object. That is kind of more important tomorrow when we start involving friction and air resistance and stuff like that. But when you are in free fall, such as this scenario over here, you're sitting in your chair, just falling, gravity is the only thing acting on you. When you're sitting down like this, you feel weight on your body, all right? That's the normal force, and that's gravity acting together on your body. So that is our lesson today about forces. You might want to check out your textbook for any questions, extra questions you might have today. But you have a worksheet which involves using the Newton's first and second laws there, kind of some ideas with inertia, and mass or force equals mass times acceleration. So give that a try. If you have any questions, send me an email. Thanks for watching.